Hi physics students, and welcome back to another edition of Rapid Review for Honors Physics. Today our topic relates to vectors. We're going to be using vectors for a lot of problem solving. I'd like to talk about what vectors in 2 dimensions implies and why it's powerful. So we know how to do up and down problems. We've done them a lot. You have initial velocity 0 or whatever you're given. You can solve all kinds of things using kinematics in 1 dimension. Easy. Also, we know left and right. We have done a lot of problems left and right. When we first introduced acceleration, we said plus x is to the right and minus x is to the left. We'll continue to do that. You know how to do these problems. But what if you end up with something where you have both? This basketball toss is neither up and down nor left and right. And what makes it worse is when something is tossed, it keeps changing direction. Watch the motion of this ball when I toss it, right? It moves in this arc shape that we're going to later learn is a parabola. And the direction it's moving, it starts out moving this way. I'll make this my vector. And then eventually it's moving this way, and then it's moving this way. It keeps changing. Isn't that ridiculously complicated? It seems like it would be, but there's a way to deal with it. And the way we deal with it is to split up our problem into up, down, and left, right. And if you know how to do that, you'll already know how to solve any physics problem using kinematics in 2 dimensions, because here's how you will do it. You'll take your vector, like say your initial velocity, you'll separate it into its y piece and its x piece. And once you do that, you know what to do with those pieces. We'll see some examples of that in a minute. Let's talk about what the meaning of this is. If I take a velocity vector v, shown in the dark color here, the dark purple, and I want to see how much x-ness and y-ness it has, I can find its components. The way I like to think about this is almost like there's a big bright light, like the sun shining, above this arrowhead, and it's casting a shadow down on the x-axis. That would be mathematically called a projection. That's your x component. And then on the left side, similar thing. I put a big sun on the left side, and I shine my light, and I cast a shadow, and that's my y component. What's more important, though, is the meaning of this. What it says, and I'm going to use velocity here again as my example, if I have something that's moving in this direction, it has some upness to it and some rightness to it, right? From your perspective, this is right. Yes, I've got that right. At the same time, it's moving up with some velocity, which we can figure out, and it's moving to the right with some velocity. If you combine them together, it's moving that way. Okay? So let's talk about how to do the math. We're going to try to find those components, the x component and the y component. That's a buzzword, as you well know by now. And we can find that by using geometry. So if we look at this picture on the left side, finding the components of something that's magnitude 10, angle of 30 degrees, we can use geometry and trig to find that. Here I use trig, and I'll let you look at that example. You've probably practiced this before. If it's not familiar, convince yourself through your knowledge of trig that this is correct, that I can find the components using those equations. Likewise, I can go the other direction. So on the right side, I have components, and I want to find the resultant vector. Somebody gave me the 5 vertical, the 8.7 horizontal, and asked me to find the magnitude and the direction, theta, of this vector. And I was able to do it using the equation shown. I used an inverse tangent function here because the 2 sides of the triangle were given. Again, if that's familiar to you, great. If it's not, you'll want to practice that and get familiar with it. The slide I just showed you is everything you need to know about the math for solving projectile problems. It's a really important basic skill that you're good at both sides of that slide. If you know that, you're home free. I've implied here, going back one slide here, that there's two ways to describe a two-dimensional vector. You can either think of it as magnitude and direction, as I show on the left side of this picture, or in terms of its vector components. Either way is a legitimate way to describe a vector. You always get to choose. You can describe it in terms of its components, or you can describe it in terms of magnitude and direction. You always need two numbers, right, because it's two-dimensional motion. Magnitude, direction, right. X component, Y component. Yep, that's two, right? So two-dimensional motion calls for two answers. Now, what do you do with all that knowledge? You can solve any problem in 2 dimensions by doing the following. First, this is the big recipe, and it's not hard to remember. First, you separate the vectors into their components. I showed you an example down below. Then, you solve the x direction and the y direction separately. This is amazing that this is possible to do, right? You can solve the y direction like the problems you already know how to do with g as the acceleration. And the x direction is even easier, right? Because there's no acceleration in the x direction. So separating them into x problems and y problems makes them very manageable and uses skills that you already have for problem solving. Finally, at the end, step 3, if you are required to express your resultant vector in terms of its magnitude and direction, you can recombine your answers using the mathematics on the important slide we looked at earlier. So that's the recipe for solving 2D, two-dimensional, that is, kinematics problems. There is some examples in the presentation. I bet you're very good at this already, and I am just anxious to get into the topic of projectiles and problem solving in projectiles. That'll be one of our future topics.